entire discussion now, I have specialized to some particular Lorentz frame, the local Lorentz frame of particle A. And I now want to ask what happens if I do the same exercise in somebody else's Lorentz frame. In other words, what is the behavior of this gravitational wave field under changes of under Lorentz transformations? I wouldn't have to ask that at all if what I were really focusing on as the main entity in terms of which I described the gravitational waves was the Riemann curvature tensor. I guess I no longer have it here. So if I discuss the gravitational waves entirely in terms of the Riemann curvature tensor, this is a geometric frame independent tensor. And you can do the entire discussion without any coordinates at all, and that's nice from the point of view of principle. But on the other hand, if you want to actually analyze gravitational wave detectors, it's really very useful to introduce a reference frame in which the gravitational wave detector is at rest and talk about it in terms of those components. And so it's because we want to do applications where we have a preferred reference frame. That's why I have gone through this process of introducing these auxiliary concepts. But having done that, then I want to go back and ask, what does the fact that the Riemann tensor is geometric and frame independent say about the behavior of the gravitational wave field, H, transverse traceless, when you change reference frames? In other words, if I look at the components of the Riemann tensor in a particular reference frame, and then I do a Lorentz transformation on them using the usual Lorentz transformation techniques to get the components in some other reference frame, what will that Lorentz transformation imply for the behavior of H? So that's a question. It's a question that we need to understand. It's a dirty question that you wouldn't even ask probably if you were a mathematician, since you wouldn't want to ever go to a special reference frame. But we find special reference frames useful, and so we find H useful, and so we therefore need to ask this question. So the statement here was, if discuss that in terms of the Riemann tensor, then no issue of transformation, of behavior under transformations. It's all very clear. But we don't want to discuss it in terms of the Riemann tensor. We want to discuss it in terms of H plus and H cross. Let me go to them because they are the ultimate things that we will generally use in our discussion of gravitational wave detection. So in terms of H plus and H cross, what happens when you change reference frames? So a change of reference frames entails two kinds of changes. One is just a rotation of the spatial axes, and the other is a Lorentz boost to a frame moving with some other velocity. And so let me begin with rotations. And let me discuss this by analogy with the electromagnetic case. In the electromagnetic case, we can discuss the entire gravitational wave in terms of the electric field. Let me take the z direction to be going into the board. And so the electric field has components Ex and Ey. The electric field is entirely transverse, just like our gravitational wave field is entirely transverse. The electric field is just a vector that lives in this transverse plane, the xy plane. Let me draw that vector in some other color. Draw it in orange. We know that if we rotate our axes through some angle theta, So we have a new x nu and y nu. Then in the new axes, the electric field Ex nu will be the old electric field components times the cosine of theta plus Ey times the sine of theta. And Ey nu is Ey cos theta minus Ex sine theta. That's all very familiar. That's just the behavior of a vector in this two-dimensional transverse plane under rotations. In the gravitational wave case, you can deduce the analogous behavior by going from H plus and H cross back to their definitions in terms of H TT, XX, YY, and so forth, wherever that was up here. So go back to these definitions. And this HJKTT is just a second-rank symmetric trace-free tensor field. And so you can just apply the mathematics of rotations and deduce how do H plus and H cross behave. That's a straightforward calculation in the rotation of the components of a tensor field. And the bottom line is that the components behave in the following way, that H plus nu under this same rotation is equal to H plus, the old one, times the cosine not of theta but of 2 theta plus H cross times the sine of 2 theta. And H cross nu is equal to H cross cosine of 2 theta minus H plus times the sine of 2 theta. So it's identically the same in the electromagnetic case, except that instead of transforming with an angle through theta, with the angle theta, it transforms with the angle 2 theta. And if this were a neutrino field, you would transform with 1/2 the angle theta. And you recognize that it's 1 here because the photon has spin 1, it's 2 here because the graviton has spin 2, and it's 1/2 in the neutrino case because the neutrino has spin 1/2. And this is then the mathematical version of something I alluded to in the introductory lectures about inferring the spin of the underlying quantum particle from the behaviors of the components of the gravitational wave field or the electromagnetic wave field under pieces of the Lorentz transformation. Okay. Mathematically, why is it 2 theta there and 1 theta here? Well, mathematically, it's because if we go back to H plus and H cross, there are 2 x's when we express H cross in terms of components of this second-rank symmetric tensor. And it's those 2 x's and 2 y's that, when you go through the mathematics, leads to this 2 theta appearing here. But you also see it equally well in terms of the stretch and squeeze, that you only, for the instantaneous field, you only have to rotate through 180 degrees to bring the instantaneous squeeze ellipse back to where it started in this case. Whereas in the case of an electromagnetic wave, where the basic thing is this electric field which is accelerating an electron in that direction, say, or in this direction, you have to rotate through 360 degrees to bring it back. So the fact that you get a 2 theta is because of that difference in the return angle for the instantaneous fields. Any questions? Okay. Next issue is what happens to H plus and H cross under a boost. Now we know that, and for simplicity, I just want to deal with a boost along the z direction, the direction in which the waves are propagating. You know that in general, well, you don't learn anything terribly interesting if you boost along some other direction, and you can boost along get a boost in arbitrary directions by combining rotations and boosts. And so I just don't want to deal with other directions. I want to deal with the simplest case and the case that really teaches me what I would like to understand. And so for a boost along the z direction, the direction in which the waves are propagating, the electric field, of course, gets transformed in a manner that involves the magnetic field, but the magnetic field we know is equal in magnitude and orthogonal to the electric field by the properties of plane electromagnetic waves. But that transformation is non-trivial, and you wind up with the x component of the electric field transforming in a manner that carries the information about the change of energy of the photon, about the as the photon propagates. And so you get a change in the electric fields. And I just remind you of that. Now I'm going to tell you that in the gravitational wave case, there's an exercise that if we discuss the gravitational wave case in terms of the h's, under a boost in the z direction, h plus nu is identically the same as h cross nu at the same event in space-time. Okay. And so if I pick an event in space-time, and so let me draw my axes. Here's t, x, y, and I'll talk about it at this event in space-time. I do a boost. I'm sorry, let me do t, x, z. I'll do a boost in the z direction, and so I have a t nu, a z nu. And I look at this same event, and I ask, now, as seen in the new reference frame, a reference frame of an observer who's moving along this world line, what is h plus, which is associated with stretch and squeeze along the x direction? Remember, under a boost in the z direction, the x component, x coordinates of particles don't change. Okay, so you have a common x-axis. X is the same thing as x nu, but the z-axis and the t-axes have been changed. The statement is that at this event, where I wanted to know what is the value, the numerical value, 17 or whatever it is, of h plus nu. The value will be the same as the value of h plus nu will be the same as the value of h plus old. Doesn't change. Well, you should have screamed. You should have shouted. What are you doing? I mean, you shouldn't sit there and allow me to get away with things like that. Pardon? You were shouting.
In our heads.
Yeah, well, your heads. I have not yet learned to read your minds. I'm working on it. Okay. So H plus doesn't change. By contrast with E plus, which does, associated with the change of the photon momentum. You know, H plus is related to the Riemann tensor by a couple of time derivatives, wherever it was I defined. So it's the same thing as HXX, transverse traceless, which is related to components of the Riemann tensor by a couple of time derivatives. And so, in fact, the components of the Riemann tensor will change. It's just that we happen to have found a particular mathematical way of describing the gravitational wave where we have identified a quantity that does not change under boosts. So it's really a nice quantity to use. Later on, either Wednesday or next week, I will talk about the energy and momentum carried by a gravitational wave, and we will see that the gravitons experience the same boosts of their energies when you go from one reference frame to another. The same Doppler shifts of their energies. Pardon?
There's no red shift.
No, there are red shifts for the gravitons. And there are red shifts also even here because Z nu is equal to gamma z old minus beta t old. And t nu is equal to gamma t old minus beta z old. And so these have numerical values that are identically the same at the same event. But if you express h plus old in terms of the old coordinates, or let me start to say it differently. If you express h plus nu in terms of the new coordinates, it's a function of, so h plus nu is a function of t nu minus z nu. That's the same as h plus old at the same event, but at the same event, z old and t old have changed. So it's h plus old at t nu minus z nu is gamma times 1 plus beta times t old minus z old. That's the same thing as t nu minus z nu. This is just the Doppler shift factor. So there is a Doppler shift when you recognize that the space-time coordinates are different in the two reference frames. But if you ask about the numerical value of h plus nu at this event, if it was 17 in the old coordinate system, it'll be 17 in the new coordinate system. But the phase fronts of the waves will have been squeezed or expanded depending on the whether you went to a reference frame that was moving with the wave or against the wave.
Electricity, the energy depended on the field strength and the frequency, but in gravity waves, it's just
when you do it in terms of h plus, it's only the frequency in here that is appearing. The numerical value of h plus doesn't change. Now, we will understand these issues a little more clearly when we do geometric optics at the next lecture or the following one. And we will see quite clearly how things are behaving. But I am going to give you an exercise to find a quantity in the electromagnetic case that has this same kind of behavior. So you can describe the electromagnetic field also in terms of some quantity that behaves like a scalar under boosts. All you've got to do is take some time integral or time derivative of the electric field or something like that in order to avoid this change in the strength of the electric field. You just work in terms of another quantity. So that's an exercise for you. There really is a close analogy between the two. But in the case of gravitational waves, and because of the nature of our detectors, we have introduced a particular quantity to describe the gravitational wave that has some particularly nice properties that you don't normally see in the electromagnetic case because you happen to use a different set of variables in the electromagnetic case. But you could find a set of variables that would have similar properties. Okay, questions? Okay. There are fancy words associated with this. When you write it in a little different notation associated with what's called Newman-Penrose formalism. The statement is that H plus and H cross behave under rotations with spin weight 2. Whereas under boosts, they behave with boost weight 0. And so there is a very fancy mathematical formalism called the Newman-Penrose formalism that is used by the real elegant mathematicians when they, or mathematical relativists when they work with this subject. And in their language, then there are particular formulas that are the analogs of these, and these are the words that go along with those formulas. Boost weight 0 means this behaves like a scalar field under boosts. Spin weight 2 means that you have this factor of 2 theta that appears under rotations. or it means equally well that you have this quadrupolar pattern in the force lines or in the squeeze ellipse. Okay. Okay, I want now to back up and talk about gravitational waves, again the same weak waves propagating through flat space-time from a different point of view. This entire discussion here is different from what you will find in any textbook, except the Blanford-Thorne textbook that I'm referring you to which is not published. It is different because it begins with the Riemann tensor right from the beginning and says we're going to work with the Riemann tensor, and it gets very quickly to the heart of matters. But in any other textbook that you look at, you'll find gravitational waves discussed in terms of the metric perturbation associated with the gravitational waves. So I now want to go over and make connection with that particular point of view. I want to do so because, particularly, not just so you can read the literature, but because when you are computing gravitational wave generation, it is more useful to work in terms of the metric perturbation than directly in terms of the Riemann tensor. But the key reason that I didn't want to begin in introducing the subject of the metric perturbation is because the metric perturbation is very gauge dependent. And it's hard to unravel out of the metric perturbation the dynamical degrees of freedom of the gravitational wave field, that is H plus and H cross. Whereas the Riemann tensor, you get to them almost immediately without any issues of gauge dependence coming in. But having now seen the basic physics of the gravitational waves and mathematics in the language of the Riemann tensor, but having boiled it down to the two gravitational wave fields, H plus and H cross, associated with the two polarizations of the waves, I now want to go back and discuss the same subject in terms of metric perturbations. So I want to treat the same problem as I was treating before, the problem of a weak wave in a background flat space-time, so that the only curvature is that of the wave. I want again to introduce the global Lorentz frame, but I can't really quite do it. I can only do it at zero order before the wave is present, and so I want to introduce a global coordinates that are as nearly Lorentz or Minkowski as possible. As possible in view of the fact that the gravitational wave is present and is curving space-time, so you really don't have flat space-time, so you really can't have Minkowski coordinates or a global Lorentz frame. In this case, then, the quantity in terms of which I want to discuss the gravitational waves is the metric, and the metric will be the flat metric plus some very small deviation from the flat metric, which I will call H alpha beta, not to be confused with the HJK transverse traceless. Okay. So set aside the entire discussion previously and begin over again, and here H is defined as the perturbation in the metric. We can then go in and ask about the Riemann tensor, which was the thing with which we began before. And you have, in the problem set that I have given to you, you have worked out a formula for the components of the Riemann tensor when, in terms of the components of the metric, when you have weak curvature, so you can ignore nonlinearities. And that formula that you worked out, and that was also in the reading, is 1/2 G alpha delta comma beta gamma it's the first and fourth, and then the other two, plus G beta gamma comma alpha delta minus G alpha gamma. This is now the first and third, and then the other two, beta delta minus G beta delta comma alpha gamma. So 4 terms is what the Riemann tensor reduces to. This is in a coordinate basis. In a coordinate basis when the curvature is weak, and so I can ignore nonlinearities, nonlinear terms. In this case, the metric is written as the flat metric, which does not depend on location in space-time, so will not contribute to these derivatives, plus the perturbation h. And so I can just go in here, and everywhere I see a g, I can just replace it by an h. So the Riemann tensor then is written as 1/2 a set of 4 terms that merely guarantee that this has the right symmetries for the Riemann tensor. That's all this is really doing, is making sure the symmetries are correct. But it's an h with 2 derivatives on it. Now, this has an analogy in the electromagnetic case. Let me write electromagnetic on the right-hand side. So I'm going to pull this down here, minus G alpha beta comma beta delta minus G beta delta comma alpha, alpha gamma beta delta, alpha gamma, and the G I turned into an H. I want now to continue this practice of making some comparisons with electromagnetic theory. In electromagnetic theory, the analog of the Riemann tensor is the electromagnetic field tensor. The Riemann tensor is the thing that directly tells you about the relative motion, or the pushing and pulling relative to each other, of freely falling particles. In the electromagnetic case, the thing that tells you about the pushing and pulling relative to the inertial frame of a charged particle is the electromagnetic field tensor, which of course embodies the electric field and the magnetic field. In the electromagnetic case, it's conventional to write this in terms of a 4-vector potential as A beta comma alpha minus A alpha comma beta, which is equivalent to, if you let AJ be a 3-vector potential, and A0, which is minus A down 0, be the scalar potential. This is just equivalent to the statement that the electric field is equal to minus dA dt minus grad phi, and the magnetic field is just equal to the curl of A. So I'm reminding you of something that most of you will have seen in a course in electromagnetic theory. I hope I have my signs right. If I don't, I'm sure. Do I have my signs right? Problem with signs, nobody knows. Okay. So my point here in doing this is to emphasize that there is an analogy. The vector potential is something from which you generate the force-producing electromagnetic field. That is, the force-producing electric field, the force-producing magnetic field. Similarly, the metric perturbation, H, is something from which you generate the relative force-producing, the tidal force-producing Riemann tensor. So H is a potential that you differentiate twice to get the Riemann tensor. A is a potential that you differentiate once to get the electromagnetic field tensor. Okay. I don't think this factor of 2 and that factor of 1 have anything to do with spins, but I don't know. So here's an exercise. Is there any connection to the spin of the photon and the graviton? I don't think so. Okay. And so we are to think of the metric perturbation, or the metric, as an analog of the vector potential and the Riemann tensor is an analog of the electromagnetic field. Now, in the electromagnetic case, there's gauge freedom. You can change the vector potential by an amount that's A alpha nu minus A alpha old, by an amount that is the gradient of some scalar field. The scalar field is the generator of the gauge transformation. And when you do that, there is no change of the electromagnetic field tensor. The analogous statement is, I think I did check this sign, if I have it somewhere, is that you can change the 3-vector potential by the spatial gradient of this psi. You can change the scalar potential by minus the time derivative of psi. The minus sign having to do with the scalar potential is defined in terms of A0 up. But this equation is written in terms of down indices, and that a difference of up versus down gives you this sign. When you do that, there's no change of E or B. And so there must be some analogous gauge freedom in the gravitational case. And it's this gauge freedom and the complexities associated with it that may make me prefer, in defining the gravitational wave field, my transverse traceless gravitational wave field, to just begin with a Riemann tensor and forget about the metric perturbation. But now because I want to use metric perturbations as a tool when computing wave generation, I want to go back, introduce the metric perturbations, and now have to understand the gauge freedom. Now, the gauge freedom, in fact, in the gravitational case, it's just associated with a small change of the coordinate system. So I can introduce a new coordinate system, x alpha nu, which is very nearly Lorentz, just as my old coordinate system was very nearly Lorentz. At some event in space-time, x alpha nu is the same as x alpha old at that same event in space-time, and then plus some xi alpha to that same event in space-time. And so xi alpha is going to be the generator of the gauge transformation. But when you look at it from the point of view of the full general relativity theory, it's really a generator of a coordinate transformation. It's telling you you're putting in a new coordinate system that differs slightly from the old coordinate system, and it differs by something that can be thought of as a vector field living in the flat background space-time. Now, in terms of a picture, because the space-time is really curved, I don't have precisely global Lorentz coordinates, and so my coordinate lines may look sort of like that because of the curvature. And all I'm doing is I'm going in and putting in new coordinates, which I'll draw the coordinate lines in green. The new coordinates are just rippled in a slightly different manner from the old coordinates. And so you have this problem then with the fact that you can't introduce global Lorentz coordinates. There is no preferred way to lay down these nearly Lorentz coordinates, or nearly Minkowski coordinates, on the space-time in the presence of the gravitational wave. So you have a real problem of separating out what is physical aspect of the gravitational wave and what is just rippling of the coordinate system. And that issue is the issue of gauge freedom. It translates, when you discuss this in the language of field theory and flat space-time, it becomes an issue of gauge freedom that is completely analogous to the issue of gauge freedom in the electromagnetic case. Under this gauge change, you can show as an exercise, and this exercise is just a business of applying the formula for how the metric changes when you change coordinates. And I've given you an exercise on that in the homework that I have given to you for this past Thursday. So you just apply that formula that you derive for how the components of the metric change under a coordinate transformation. You apply it here. And the bottom line that you come out with is that the new, after this infinitesimal coordinate system, then the components of the metric perturbation have changed, and h mu nu in the new coordinate system will be the same as h mu nu in the old coordinate system, minus c mu comma nu minus c nu comma mu. Commas are partial derivatives. These coordinates are very nearly Lorentz at first order in the gravitational field, at first order in the metric perturbation, at first order in the generator of the gauge transformations. This equation can then be thought of as an equation in flat space-time, okay, linearized in flat space-time. So the gauge change here is take a gradient of the vector field that is the gauge generator, and then symmetrize. That is, you've got mu nu and nu mu. Then you symmetrize, and you subtract that off of h to get h old in order to get h nu. Whereas up here, what you did was you took the gradient of the scalar generator of gauge changes and you add it on. The issue of adding versus subtracting is just a convention of how I chose to define my signs. Okay. So it's very similar. This really is the simplest thing you could imagine for a gauge change, since this is a second-rank symmetric tensor field. If you wanted a gauge change that involved a gradient, the only thing you can do is take the gradient of a vector field and symmetrize, then add or subtract, depending on your conventions. Okay. But the physical origin of it is this rippling of the coordinate system. Okay. And so I want to finally wind up with a very important theorem or remark that you again will prove on the problem set I'll give to you on Thursday about the relationship now between this description of the gravitational and this description that came from the Riemann tensor. And this theorem says that there exists a gauge change or gauge specialization for any gravitational wave or any weak gravitational wave propagating through an otherwise flat space-time. So there exists a very special gauge for such a gravitational wave in which h, the metric perturbation, h00, hj0, h0j, these are equal by symmetry, vanish. So the only non-zero components are the space-space components. And h space-space is identically equal to hjk transverse traceless, the gravitational wave field that we defined originally in terms of the Riemann tensor. This gauge, this special gauge corresponds to a very special choice of the coordinate system. You have organized the ripples in the shape of the coordinates in a very special way in order to guarantee that this is true. And so these coordinates, are called transverse traceless coordinates. This gauge is called transverse traceless gauge. In the language you use, coordinates or gauge is just an issue of whether you're thinking of yourself as doing field theory in flat space-time when you discuss these gravitational waves, in which case you use the language gauge. But if you think yourself as doing an approximation to general relativity and space-time is really curved, then it's this, you think of this in terms of having specialized the coordinate system. Okay, I'll continue this on Wednesday.